So there's this bead, and you could think of it as it's just a mass that's able to slide along a hoop, and we will rotate the hoop about the vertical direction. So gravity is pointing down. You can just kind of see if we were to release this from rest and with the slow enough rotation of the hoop, the marble just sort of rolls back and forth like a skater in a half pipe. Nothing too exciting there. But things get more exciting when you speed up the hoop. We'll derive this using Newton's laws. It's rotating about this vertical axis with some frequency omega. What we want to do is jump into the frame of the hoop. We'll assume that it's a circular hoop. We've got the hoop rotating with respect to an inertial frame with some frequency omega. Just like we would a pendulum, we would track the angle with respect to the downward position. We'll track the angle of the bead, which is here, with respect to the downward position. So that's our angle theta. We'll use a frame that's centered at the center of the hoop. We'll call that our origin O. If we write Newton's laws for the bead as observed in the hoop is this frame that's rotating around. If we attach a frame to the hoop, it's a rotating frame. Let me write some forces over here. There's a downward gravitational force that's equal to m, the mass, times g, the acceleration due to gravity. All we're going to care about is the tangential motion. So meaning the motion in the theta direction. I'll call that motion in theta. So that's tangent to the hoop. So that means we could take the forces operating on the bead and just project them into the local tangent. So we'll take the force due to gravity and project that. This will be an angle theta as well. There's also the force, you could call it the centripetal or centrifugal force. You spin something, there's a force pushing outward, and it's proportional to the distance from the spin axis. So this little blue dashed line, we'll call that rho. The hoop has the radius r. There is an outward force due to the centrifugal force. It's proportional to the mass, and then rho is this distance from the axis of rotation times the angular velocity squared. The value of the angular velocity is omega, so we could put a omega squared. We'll also assume there's some kind of friction. It's actually pretty hard to model friction. We're going to assume friction resists the motion of the bead along the hoop, so we'll make it proportional to theta dot, but opposite theta dot. If the bead is actually going this way, say theta dot is greater than 0, then this force will be negative b theta dot. So it's just like a viscous drag. It's a tangential damping force. Taking g is greater than 0 and b is greater than 0. M is greater than 0. Omega is greater. All these things are greater than 0. R, of course, radius of the hoop greater than 0. From the geometry here, we could work out what rho is. This is perpendicular, and this angle is theta. So rho is actually r sine theta. We're only looking at the tangential motion, so we could project the centrifugal force onto the tangent plane. What we'll get is that Newton's laws, which is mass times acceleration equals the force, we're only looking in the tangential motion of the bead along the hoop. That component will give us mass times acceleration, which is mr theta double dot, equals the forces projected onto here. If we look at the forces, the force of gravity projected onto here give us minus mg sine theta. The centripetal force is m rho omega squared cosine theta. Plug in what rho is, so we get mg sine theta plus mr omega squared sine theta cosine theta. Oh, and I forgot to put the drag. It's going to be minus b theta dot minus b theta dot. Maybe I'll move these things around. There's no sine or cosine on this term because it's already tangential by assumption. So our equation of motion is this second order ODE in theta minus b theta dot mg sine theta plus mr omega squared sine theta cosine theta. It's interesting that some of these terms have negative signs, some have positive signs. So it sort of suggests as we vary the parameters of the system, we could get different types of behavior. So maybe we'll get a bifurcation at some point. What else can we say about this? look at this. It's nonlinear. So this is a nonlinear, it's second order because the highest derivative is second derivative. So it's a second order ODE for the variable, right? That's the thing that can change in time, theta. Terms like this are linear. Terms like sine theta are definitely nonlinear. Nonlinear. Sine theta, cosine theta, definitely nonlinear. So it's a nonlinear second order ODE. We've got the variable theta that changes with respect to time, t, which is buried in these things like theta dot, right? What's theta dot? That's d theta dt. Theta double dot is second derivative of theta with respect to t. We've got parameters following the terminology. These are things that for any evolution of the system would be left constant. How many do we have here? We've got m. The radius isn't changing. B, G, omega. We got 5 parameters. So we might go, oh, wow, if we wanted to study this system, we'd have to do this exhaustive search through a 5-dimensional space of parameters to find out what the qualitatively different types of behavior are for this pretty simple looking system of a bead and a rotating hoop. But we will simplify it using dimensional analysis.